Hi everyone, this is Chen Hong, and I'm going to present our work, Deep Learning-Based Near-Orthogonal Superposition Code for Short Massive Transformation to the ICC 2022. This work is proposed for the massive machine-type communications. As we know, 5G technologies is comprised of three parts, namely EMBB, URLC, and the MMTC. So the machine type communications are typically employing short messages and short packages carrying a relatively small number of information bits for the communications in the electronic devices. However, the conventional channel codes designed for large block lengths is less effective in such short block length region. They usually exhibits a high error floor or non-neglectable coding gain loss. Among these modern codes, these polar codes with CRC is proven to be more reliable, as we can see in the right figure. So the motivation of our work is that when we notice that the modern codes are less effective in a short package length, that is around 32 information bits, we wish to invent some new codes for the massive machine type communications. The prior works for our work, the prior works is the HDM, which is the hyperdimension modulation. It is a special form of superposition code. As you can see in the right figure, it is comprised of position modulation, the symbol modulation, and then it performs the FFT transformation and the permutation transformation to get each code word. And then we sum up these such code words together to get the superposition code, which will be transmitted through the channel. This kind of superposition code can outperform the CRC-aided list decoding polar under short block lengths. And you can see from the right figure that is under 64 information bit and code rate equals to a half. The HDM outperforms the CRC-aided polar codes by 0.5 dB. So even though the HDM gives us impressive performance, the encoding scheme of it is assumed to be FFT transformations followed by random permutations, which is efficient because of the FFT transformation, but it does not necessarily to be the optimal coding scheme. So our work is going to combine deep learning and the superposition principle to seek better learned codebook to achieve even better reliability and efficiency. So the left figure is the neural network structure for our paper. For the encoder, the encoder is comprised of these sections, and each section is comprised of a linear layer and nonlinear activation functions, followed by the power allocation and the power normalization layer at the end of each section. The input to these sections are the one-hot vectors, and each one-hot vector has dimension m, which conveys log to m number of information bits. Each section will output a d-dimension signal, which will be summed up and pass the AWGN channel. At the decoder, it still consists of these such sections, and each section takes the received signal y as input and outputs a probability vector P1 to PV. The loss function for this neural network is defined as the cross-entropy loss, which we calculate the cross-entropy loss between the X1 and P1, the cross-entropy loss of X2 and P2, and then finally the cross-entropy loss between XV and PV, and then we sum them up together to be the total loss. We backpropagate the gradient and optimize the encoder and decoder all together. So after training the above neural network for enough number of epochs, we can obtain the codebook properties. So we define the codebook as C, which has shape V, M, and D. We determine the intercorrelation and the distance of the code words in C. And to be processed, the intercorrelation is defined as the inner product between the code words belonging to different sections. And you can see that here, I and J, they are different. And we will calculate for all these pairs belonging to different sections. And the left figure is the plot for the distribution of the intercorrelation. You can see the x-axis is the correlation in dB, and the peak value is around -30 dB. So that means that the inner product between the code words belonging to different sections is near zero, and that is why our title is Near-Orthogonal Superposition code. For the distance property, we only estimate the L2 distance between the different code words belonging to the same section. And you can see for different combinations of B and M, this distribution will be somewhat different. And we will discuss it in the following slide. So just as the CRC edit list decoding polar codes, we wish to enhance the PR performance of our proposed unknown S code with CRC. That means we need to construct the candidate list with size K. And that is to find K such combinations which maximize the posterior probability. And given the superposition nature of our code, and given the channel is the AWGN channel, the maximizing the posterior probability is equivalent to minimizing the L2 distance between the received signal Y and the summation of the code words. We have encountered such searching problem in the memo detection, and we can use these algorithms like K-best decoding algorithm to our scheme. Moreover, by finding that different code words belonging to different sections, they are near orthogonal, we can dramatically reduce the complexity in calculating this matrix. So when we expand this L2 distance and apply the near orthogonal approximation, we can get this equation. And note that the Y is known to the receiver, and these code words are carefully normalized. We will only focus on this term. And finally, we will need to find out case of combinations which maximize this inner product between the received signal Y and the code words. And we will solve it in the next slide. So for the K-best decoding algorithm in this paper, we start from the root of the tree, which has a matrix equals to 0. And then we calculate the matrix for the first layer. And then we prune the branches with small matrix and preserve the branches with large matrix. And then we extend the survived K branches. And then we calculate the matrix for the second layer using this equation. And then we still choose the K largest matrix and prune the others. And then the K survived candidates at the second layer is obtained by extending, calculating the matrix and then pruning. We can get the top K candidates in the final layer of the tree. And these candidates will be further examined by the CRC. So before we discuss about the final evaluation part, we will discuss how to adjust system parameters to achieve a good PR performance for the unknown S code. So as we have discussed before, The NOS code can be determined by the parameters V, M, D, and K, where K is the number of candidates to be preserved in the K-balanced decoding algorithm. So consider a case when the number of information bits is fixed and the block length D is also fixed. Actually, there can be different combinations of V and M to be chosen. And we need to identify the strategy, the optimal strategy to select such V and M combinations. So we will explore this via Monte Carlo simulations as shown in the left figure. And we can see that when V equals to 6, it is the best. It has the best PR performance. And the reason behind it is because the distance distribution for V equals to 6, M equals to 2048 is the best among these three. Specifically, the V equals to 6 has the largest minimum distance in these three combinations. And actually, we would also be interested in examining in testing even more smaller V, that is V equals to 5 or even 4. But note that when V equals to 5, M will be very large, so it will be unfeasible for the real applications and for the decoding complexity. So we just keep the M equals to 2048 for the whole simulations. And finally, it is the evaluation part. So given that the CRC edit polar codes is very reliable, so it serves as a baseline for the comparison. So in the left plot, we have the polar code to have 32 information bits. The code rate equals to a force, and it is QPSK modulated. The list size equals to 8, and the information base is protected by 11-bit CRC. While for the NOS code, we have V equals to 3, M equals to 2048, and that means it has 33 information bits. It has the same amount of channel use, and the K equals to 128, the CRC equals to 11 bits. So as you can see in the left plot, the NOS code outperforms the polar for near 0.5 dB, which is quite impressive. However, when you are gradually increasing the number of information bits transferred, you can see that the dB gain from our NOS code is shrinking. So you can see that the NOS only outperforms the polar by a small margin. And by further simulations, we found that for the information base equals to 64 dB, the NOS code is just overlapping with the polar. So that means that our NOS code is good at the block length from 32 information bits to 40 to 64 information bits. And beyond that range, it might be outperformed by the modern codes and the other codes. And finally, it is about the running time. So as described in the previous slide, the NOS property, the near-orthogonal properties simplifies the matrix calculation quite dramatically. So we can calculate the matrix by using simple summations. So that means we can process the scheme all in parallel within a layer, which accelerates the progress. And moreover, in these simulations, we observe the running time for the NOS code is about 5 times shorter compared with the polar code simulated in the MATLAB on a desktop CPU. We will provide the complex analysis in a journal version of the paper, and we will leave the scalable problem for this NOS code in the future. So that is all for this ICC paper, and thanks a lot for listening.